Hey guys, so it's been a little while since the last time that I posted one of these videos, but I am really excited about this series. I'm excited to teach you today about decision trees. I've been able to upgrade a lot of my setup since the last time that we talked, so hopefully the audio is a little bit better and same with the visuals. But I am still using the same footage from when I originally recorded while sklearn. So let's just hop right in. Let's go learn about decision trees.
All right, here's our first graduation. And you can see in here we get these cute little sticky notes to commemorate our journey. And we can review the comics and or this gives us a nice little overview of what tasks are available. Okay, so next part, how to recognize a cat in the picture. Hey, is there any way to detect a cat without using expert systems? It works for text, but with pictures, not so much. Furthermore, the cat won't sit still. That it does not. Try decision trees. Those are like expert systems, but on steroids. Once you feel comfortable around them, try SIFT. This little devil is way more effective with pictures. Also works nicely when paired with other algorithms. Nice. Or you can use nails or glue or something. Come on, it's just a cat. It won't fight you back. I'm just kidding. Please don't use anything I mentioned on an actual cat. So, okay, different nodes have different processing rates. You can see this is 0.3 seconds, this is 1 second. That parameter will influence the efficiency of our schemes and how long it takes to process things. So, okay, let's talk about decision trees versus expert systems right now. So, decision trees compares output parameters with an element's color in the game. In real life, you've seen them before. They're kind of like the basis of flowcharts. You have one node that represents a yes-no architecture, like, are you awake? Yes, no. If you are awake, time to work. If you're not awake, time to sleep. Really easy stuff. And you can make those decision trees much bigger and much wider, and they can have more than just one option coming out of them. But each node in the tree only has a limited number of options, and there are only a limited number of options down at the bottom. Normally that's going to be 2 or 3. For each element, the tree asks some questions and chooses a class most similar to the element. So video, you guys can look at those, all will come in the description. So if we get this decision tree color. So this is our first problem where we really need to think about it. We have 2 categories that we're allowed to split. We have, I guess, two nodes that we're allowed to come off of, and we have 4 categories that we're allowed to touch: red, green, blue, and any. We have 3 colors, and you'll notice we want red and green over here, and blue and green over here. The best way that I can think of to do this, we'll test it out to make sure it works, is to connect red up to the red and blue down to the blue, because they share green in common. What that means is 50% of the greens are going to go towards the red, and the other 50% are going to go towards the blue. It's a nice split because the decision tree doesn't have to make a decision, in quotations, about the green, so it will just sift them one way or another. Looks like that worked perfectly. I'm just going to keep going on the regular path. Ooh, Strange Man, the Illuminati origins. Good day. I study ancient manuscripts and books in order to figure out the true story behind the Illuminati secret society. I need to recognize all the triangular shapes in these documents to solve the puzzle. Can you design a program that would do that for me? Decrease and increase speed. Okay, we've already done this. So here we get our third algorithm, SIFT. And the game does a fun little thing to differentiate between text and images. In the text is more colors and the images are more shapes. So in this case, we'll see almost the same as an expert system, but with shapes instead of colors. SIFT stands for Scale Invariant Feature Transform. It's one of the most powerful non-neural algorithms for detecting features on pictures, which is essential for image recognition. SIFT is very fast and capable of recognizing simple objects and patterns. You'll notice they keep differentiating between neural and non-neural algorithms. We'll get into that more as we're going through this. So we want triangles. We don't want anything else. So that'll go to the trash can and we'll test run. It worked. $1,000 from that. Okay, working for the man feels too easy, boring, or soul-sucking. Aim for the sky and become a CTO of a startup. In the world of savage market laws, it's either sink or swim. Will you get rich or bite the dust? It's worth trying anyway. I am not going to do that right at this moment, but I will do it later. So we're coming to our first story comic. We're 18% done with cat speech recognition, but we are 100% done with being able to recognize our cat in pictures using SIFT. So let's come out and let's see what's available here. Looks like we don't have enough money for the skins. We do have enough money to upgrade our hardware a little bit. Rentium. It's like Pentium. Nice. Let's just get all of these. The tambourine increases data transfer speed by 1%. We're a superstitious bunch of programmers, right? And then 1 megabyte of RAM. Probably some of you watching this video will remember the good old days when there was only 1 megabyte that you could use. So we have a couple of emails to read too. So history of expert systems. 1965 can be considered a starting point for the work on creating expert systems that your scientists at Stanford Research Institute, Edward Feigenbaum and Bruce Buchanan, teamed up with Nobel laureate Josh Lederberg and began working on a computer system designed to determine the molecular structure of chemical compounds. That's pretty cool. We invented the decision tree. The decision tree is one of the automatic data analysis methods. The first ideas of creating decision trees date back to the works of Hovland and Hunt in the late 1950s. However, the fundamental work that gave impetus to the development of this direction was a book named Hunt, Marin, and Stone Expeditions and Induction, published in 1966. Cool little facts. Letter from Mom and Dad. Hello, dear. We remember how you cherish your financial independence, but come on, your birthday is just around the corner. Be a good kid and take this money and buy yourself something nice, will you? We love you very much and we miss you. P.S. Don't forget to put a hat on. It's very cold outside. Wow, okay, so that doubled our cash. Nice. Oh, look at this. Oh, that's delightful. So here's our cute little cat. Let's change. That Donald Trump cat. Halloween cat. I like the cat corgi combo, so let's do that. This looks like another copyrighted character. Here's our cute little 1 megabyte of RAM, pumpkins and stuff. So let's oh, we haven't finished enough for gold, so let's do another thing. Get that. We have decision tree equals smart tree. Okay, Spanish school again. We hope it's our last request for you. We changed our database system. Can you update your code one last time? We need it to work faster. Let's do it. So, okay, we have almost 1 full second. We have almost 0.3 seconds. Let's make it faster. Does that work? Let's see if that works. No, it does not. Here's our first example of it not working. Straight up just did not work. No. Okay. So let's do this. Let's do red and blue, so some greens will come out of. Shoot. I'm getting a call. So let's think about this real quick. Definitely want red coming out of here. Here, and then we want to differentiate red and green. So if we do it this way, the way this is working is we have red, green, and blue coming in randomly. Red and green will come here, and that's where we split them again. So only red comes out here. But you'll notice two of these, 2.97 plus 2.97, is almost 0.6, which is still faster than 0.99. So let's test run this and see how it goes. Perfect. Look at that. We're almost 6 seconds under the maximum time for gold with 100% accuracy. Doing great. Enough for gold. All right. Yeah, let's go. So Eliza's the first chatbot. We're reading and stuff. We got some cat mail. Here's an old-timey video camera and monitor. This should definitely work. It's text to cat. Hooray. The cat has been detected.
All right, so we've learned about decision trees. We used a decision tree to improve upon a previous system that we made using an expert system. And we also learned about SIFT. And I'm really excited to teach you about how to make decision trees. I debated a lot about two things. Number one, I debated a lot with myself about whether or not I wanted to teach you how to code your own decision tree or how to use an optimal decision tree effectively. And I settled for the latter. I will show you some code for a real live decision tree. In fact, the same one that we're going to be using in this demonstration. So you will have that. You will have access to it. It's open source. You're going to be fine. But I figure enough people have optimized decision trees already that it's more useful for you to be able to use someone else's and actually be able to use it well than to be able to code your own. I hope that makes sense. If you have any questions, feel free to ping me in the comments. So let's get right into it. So first off, check this out. This is colors.csv. So this is going to be really similar to what we made in our expert system. We have 3 columns. Essentially, we have the grade that a student achieved. We have the color, and this is not referring to their color. This is referring to the color within while true learn. So that could be any color. That could represent any other data point. But we have red, green, and blue. And in this case, we have 10 reds, 10 greens, 10 blues, and they're just in a random order. You'll remember from the actual exercise where we were optimizing that we wanted to get all of the reds, but we did not want any of the greens and we didn't want any of the blues. We're going to do this even a little bit more fine-grained within our example, and we are going to want only the reds who also received A's in their classes. None of the greens, none of the blues. Those are the only people that are going to be accepted into this hypothetical school so that we can get on solving this problem. So if you would like this exact CSV, this is an open office. You can do it in Microsoft Excel as well. Just make sure you save as a .csv instead of as a .xlsx or any other file extension, and you'll have the exact same one as me. Feel free to pause the video here and copy it all down. At some point, if these videos get enough interest, I am going to make a GitHub for this, so it'll be included there. Let's get into writing the actual code, though. So, hold on one second. Let me get this all ready. All right, decision tree.py. This should look familiar. Here's our expert system that we made last time. So remember, we're trying to get into MIT for this. So let's do something similar. We're only going to need 2 imports for this, which that's something that I'm trying to keep with this. I'm trying to make sure that we're importing as little as possible, keeping it as simple as possible, and still getting it done really quickly. So here we go. This is going to be a staple for pretty much all data science that you do. Import pandas. Most people like to do as PD. I'm one of those people, so we're going to do that. And then from sklearn.tree import decision tree classifier. Now, this is somebody else's decision tree. It's scikit-learn. They're an open source, and I want to show you the code right now for their decision tree. Let's just go through it really quickly. So this is scikit-learn for Python. Here's their decision tree classifier, so you can see that it's inheriting from classifier mixin and also from the base decision tree. So this is even a little bit more fine-grained than our regular decision tree, because this one is made to not just create the tree, but also predict based on the tree, which is exactly what we want, right? We don't want to just create a decision tree. We want to be able to generalize and get results on unknown data. That's the point of these machine learning exercises. So as per usual, they have a really, really long doc string with some examples right at the beginning with the iris data set. But basically we have this init. We have, here's our first function, the fit function. This is where the decision tree trains on your data and it learns to predict. It calls itself within that function. It predicts probabilities and it predicts log probabilities. Those are the 3 methods within this decision tree classifier class. If you'd like to look more at this code, if you want to copy it yourself, feel free. Again, this is all open source. So let's get into writing the actual stuff. So Pandas makes it very easy to work with CSV files. So we're going to just do pd.read CSV. And then we import we write the name of our file, so colors.csv. Please make sure that this decision tree.py is saved within the same folder as colors.csv. If it's not, that read CSV needs to contain a path to the actual file. You can't just put colors.csv and expect your computer to magically know where it is. So, and then we'll just print df. We'll go to this point. All right, so you can see down here in our terminal, let's make this a little taller. We have our CSV, grade color pass, A green no, A red yes, B red no. So we have to, as in most machine learning, actually not most anymore, but this is what we would call a supervised model. It's not a full, this is not a neural network. This is a decision tree, but it is supervised learning where we provide it with the correct answers in our data set so that it can learn from those correct answers. Decision trees end up being completely probabilistic. They're statistical. So it ends up learning the probabilities that each answer is going to be correct. That's why you can give it slightly inconsistent data and still get really good results on it. I would suggest, if you want to test yourself on this, try writing a decision tree to predict who would have survived the Titanic based on the famous Titanic dataset you can download from Kaggle or Google or pretty much anywhere online dealing with data science. That's a project for you guys, though. So we have our data frame. I need to tell you this right now, because otherwise the next part is not going to make any sense whatsoever. All of our data has to be numerical for probabilities and for decision trees. Converted to numbers, 3 exclamation points, because it's very important. So the way that we can do that, pandas has this fantastic function, or it's a method called map, which if you're familiar with JavaScript, I can almost guarantee that you've done stuff with map before in JavaScript. Python, I haven't used it as much except in this context for data science when we're converting an entire column within a CSV to numerical data as opposed to the strings, because those strings won't work. I'll give you an example in a bit of what happens if that doesn't work. So first, or if it's still in strings. So this is a standard dictionary. We're going to do A equals 0, B equals 1, C equals 2. And you can assign these whatever values you want. The values are kind of arbitrary as long as they're unique and as long as they're numerical. So here's our df grade. So this selects the grade column within our, here I'll go over with the mouse, the grade column within our CSV. Oh, and now my cursor's down there. Grade equals, and so we are going to be changing this in place, meaning we're changing the actual data frame, dot map, and that map will take the dictionary that we just created, so D. What we're going to do is copy and paste this a couple of times. So the second one, we want our colors, so red, blue, and green. And this is where I mean you can assign these to whatever you want. Just make sure that the columns match the actual columns within your data frame. Color. And make sure that the values, you include all of the possible values. Yes. And then this is the one that's going to be different, and it's because it's the prediction. So yes, no. This is how we're going to be able to tell at the end, is it a positive or a negative prediction. Normally we want positive to correspond to 1 and negative to correspond to 0 within a binary classification. But I mean, you can flip that just as long as you understand what's coming out of this at the end of it all. Pass. Okay. So let's print this again so we can compare to what it was before. You see, what we've done is we've changed the data frame to represent numerical values. Whenever in grade we had an A, that corresponds to a 0. Color we had a 2, that corresponds to a green. Pass we had a 0, that corresponds to a no. Meaning it was a green color that got an A, but because they're green, they're not going to get into MIT. It's weird that this color was probably not a good thing to do for students. It feels weirdly racial, but I hope you guys know this is not my intent at all. Okay, we're just gonna keep going because I don't want to come up with a new way of doing it. So, features. This is where we define a list of all of the column names that correspond to our features. What are our features? In this case, we have color and we have grade. Is pass a feature? No, we're trying to predict pass. So features corresponds to everything that we're not trying to predict. So in this case we have grade and color. X equals df, and then we can pass in this list because it's the 2 column names. So X will correspond to all of the columns defined within that list. Y is going to be pass, so the column that we're trying to predict. You should be at least familiar with the concept that X is what we're given and Y is what we're predicting. Just as long as you get that, then we're good. So let's see. Our decision tree is going to be, we're going to instantiate our class, the classifier. And then we are going to train on our data. And it's really easy. You pass in the list of features, and then you pass in the column that you're trying to predict. So the labels, the features, and then the labels. And let's run this just to make sure that it actually does run up to this point. Okay, perfect. Now we can get into predicting things. So I've got 4 predictions that we can do here. I mean, you can play around with this as much as you want, but these are 4 that I came up with that I feel like help us. Green. Okay. So the way that we can actually predict on here is normally you would assign a variable to this. Yeah, I'll show you that on the first one, and then going down through them, we're just going to print it out. But so we'll say like y hat, as in the predicted label. Yeah, we'll just call it y. Y equals tree.predict, and then this predict is going to take, make sure you put 2 brackets to show that it's a series, not just a list. So a red is 0, 0, and then print y. I'm going to name it something else because we already have y in here. Let's call it z. That's nice and easy. Let's print that. Okay, z is 1. All right. So you understand this is how you would assign it to a variable in order to work with it further, maybe get more predictions out of your first prediction. That's how you would start building a series of decision trees to make really complex decisions. So print tree.predict, 2 brackets, and we want 2, 0. And I'm gonna just copy and paste this and just change the numbers a couple of times. So A is 0, blue is 2, C is 2, green is 2. Okay, so let's check out our predictions and make sure it's getting stuff right. Wow, so just on 30 examples, it's getting this right. Admittedly, it is really simple, but because we're filtering out everything except for the A's who are red. But, so it predicted a 1 for the A's that are red. It predicted a 0 for everything else, meaning our decision tree is actually working properly. You can use this same algorithm to predict pretty much anything that has a solid workflow. Like if you can guarantee that 100% of the time when this is yes, it needs to be this thing, and 100% of the time when this is no, it needs to be this other thing. Otherwise, your accuracy on decision trees is going to start going down. That doesn't mean that they're not useful. You can still use them in a lot of situations, but I just want to warn you of that beforehand. If you can't guarantee that it's a 100% binary split between yes and no for each of these questions, then your accuracy is going to go down. I hope that you enjoyed this video. I hope that it was illuminating, and I hope that this decision tree helps you out. I will see you later. I'm working on another one of these videos tonight. Feel free to like and subscribe. I'd love the support.